Hello, everyone. Welcome to today's IAIFI Colloquium. It is a pleasure to have Yasaman Bahri here. She's joining us from Google Research. Yasaman's PhD was out of Berkeley with Ashwin Vishwanath in 2017 in condensed matter theory. And then she joined Google shortly thereafter and has been doing wonderful work in theoretical deep learning since then. And she's going to tell us about it today, casting it in, under a broad framework of trying to understand deep learning. And Yasaman, it's wonderful to have you here. Please take it away. There will be questions at the end. And if anyone's listening on YouTube, please feel free to post questions in the chat there, and I can bring them to the Zoom meeting at the end. Thanks.
Thank you, Jim, and everyone for joining and for the kind invitation to give a talk here. So I wanted to talk pretty broadly about an area of research that I've been working on with collaborators at Google, trying to understand deep learning. And so what do I mean by understand? I mean something a bit different than what has historically been done in machine learning theory, where there's been a focus on, say, statistical or algorithmic guarantees, but trying to understand in the way that we do in theoretical physics, trying to gain insight into mechanisms that are broad and kind of universal within deep learning, and also trying to develop theory that might have a hope of matching with experiments. And this is kind of a challenging thing to do because, as I mentioned, there isn't a lot of historical precedent for it necessarily. And so even finding the right set of questions can be challenging. Some questions are too microscopic. They may be the byproduct of some complex optimization process in these artificial systems. So even trying to figure out what it is that we can understand cleanly and simply with theory kind of in the style of physics is itself part of the question, I think. I'd like to spend maybe about 10 slides giving a bit of the highlights from work that I've done with a lot of folks at Google Research. It's really representative of a lot of people's work on the theory of learning in deep neural networks, and in particular, a lot of the traction that we've gained by studying kind of what turned out to be exactly solvable limits in deep neural networks that are very wide. So these are neural networks where the hidden layers, which have many hidden units, it's taken to be infinite. And it turns out that this gives rise to a correspondence with Gaussian processes or Gaussian field theory, if you'd like to cast it in that language, linear models and kernel methods, which are kind of established methods within machine learning. And then I'll just say a few words about how there's been research progress since then on studying other regimes, and that's kind of ongoing work by a lot of people. And then I'll switch gears and start talking about more recent work on trying to understand so-called scaling laws in deep learning. And some of the tools from part one will be useful in part two also. So just to set this up for folks who maybe are less familiar with the setting, a lot of what I'll say will be agnostic to the architecture. You can adjust it appropriate to the there will be architecture kind of independent statements, but if you'd like to think about just a vanilla deep neural network in your mind, it's a transformation on an input X, which lives in some d-dimensional space. There's a series of affine transformations coming from these weights and biases that are applied, and then a pointwise application of nonlinearities for some depth L through the network. So this is kind of the most vanilla version of a deep neural network. I'll refer to the collection of all parameters as just theta mu when I write some derivatives over the next few slides. So that's the model family, the most vanilla version of it that we'll be thinking about. And the setting that is often of interest in practice is supervised learning within the framework of empirical risk minimization. So you have some data set, it's of finite size, there are big D data points. You form this empirical risk, and then you just try to optimize it with something like gradient descent. so this equation kind of on the right, and you end up somewhere with some sort of solution. You do well on this problem if when you go to kind of look at this learned function on the true distribution that you were trying to learn, if your error on that distribution is actually low. So that's when you generalize well in this set. So to maybe kind of motivate what was a kind of shift in perspective around some of the early part of this work, historically, there's been a lot of focus on parameter space, just because that's kind of the focus of optimization. That's the thing that you access directly when you actually run the algorithm. And also because in the past, statistical models were often constructed to be more interpretable. So learned parameters may have had meaning, they might have corresponded to the moments of a distribution and so on. In neural networks, parameters were not really designed to be interpretable. And there's also a great deal of redundancy. So there could be exact kind of symmetries, for instance, like permutation symmetries. There's redundancy in the parameters due to after learning because of the data set and so on. And so really, the thing that you care about more is the learned function, not the parameters. The parameters are just the way you kind of access and do the optimization. So it motivates asking questions about the functions that are represented. If you could work purely in function space, you would kind of be done. You wouldn't actually need to know much about parameter space. So there was this question: what class of functions in general is expressed? So this is captured in things like the universal approximation theorem. What sorts of things could you express with a neural network if you were allowed to choose any setting of the parameters? But we want to focus on kind of the bias that actually comes about from initialization and optimization. So what class of functions is expressed at the beginning of an optimization process in the way that we usually do this in practice, and what class of functions do you have access to during the course of training? And in general, this is a challenging question, but we gained some traction by working in this infinite width limit. And there was a precedent for this work actually from the 90s. So the case of a single hidden layer had been studied then, and an equivalence to Gaussian processes had been built. And then it hadn't been worked out for the case of deeper networks. So we did this along with another group a few years back now. If you take the limit of infinite width, where this parameter n, the number of hidden units, is taken to be infinity, then you can construct this exact equivalence. So why does it come about? The reason is that typically when we initialize parameters at the beginning of an optimization process, we draw them from some prior distribution and we draw them IID. So for example, a common form that we might use is something like this. The weights might be drawn, for instance, from a normal distribution, and the biases also with some variances. It's important that this variance is scaled down by 1 over n. This is what's typically done, and this is the reason that you kind of it is behind recovery of this limit. There are other ways you could imagine choosing these variances and so on. But this is how we usually draw parameters. So that distribution over parameters gives rise to some distribution over functions at initialization still. And the main idea is that as n goes to infinity, you can apply the central limit theorem sort of successively to the internal functions computed by each layer to get that the final output of the network will be Gaussian distributed. So you could track any, say, finite collection of data points, let's say x of alpha, x of beta, and so on, and look at that distribution, the distribution of the function output on those data points as you pass it through the network in this limit. And so it turns out that collection of data points will be Gaussian distributed. That's the definition of a Gaussian process. So schematically, f in the distribution the distribution over functions is a GP. For us, because of this mean zero setting, it has mean zero, and it has some covariance function K that you need to compute. What is the expression? The expression is just computing. You want to compute this 2-point function where this expectation is over draws of the weights and biases, the parameters, and you can write down a recursion relationship for that. So f sub f to the L at the Lth layer, it's written in terms of fl minus 1, the function output from the previous layer. And you also know that that's governed by a GP. And so you can write this expression. This turns out to just be a 2-dimensional integral against a Gaussian. So, and in many cases, that's exactly computable. So you can even write down a closed form analytic expression for it. But more generally, I just will box it, this recursion relationship, in this way that there is a relationship between the covariance function at layer L and the covariance function at layer L minus 1 via some mapping that depends on, say, the choice of nonlinearities and so on. So the computation that's being done by the network at initialization in this limiting case is just captured by the computation done via these 2-point functions. And so just illustrating that a little bit more cleanly, in general, there's a recursion on the space of functions. In the infinite width limit, you only have to keep track of this recursion that's happening on the space of covariance functions or kernels. So just on the space of functions of 2 arguments. And so that gives rise to some recursion relationship. And there's a base case that you know, which just comes from a linear transformation on the x's. And so you get a dot product, but that becomes kind of very nonlinearly transformed as you push it through the network. So this is the description of the Gaussian processor, the Gaussian field theory in this limiting case. There are a lot of things then you could do with that. So you can do like Bayesian inference exactly and so on and write down exact expressions for that. That's sort of like the textbook application of inference to GPs. But what I want to now talk about is how that kind of was sort of the basis for then thinking about the problem that's really of interest, what happens under gradient descent training in this limiting case. I mean, of course, we're interested in networks that are of finite size, and I'll say a few words about that in a couple of slides, but still working in this infinite width limit. At the time, it wasn't clear, can we even say anything about what's happening under gradient descent training when we're doing supervised learning. So I want to maybe show the structure of some of the equations that come up when you think about this problem. And just for simplicity, I'll illustrate it by working with gradient flow or continuous time gradient descent. So if you work in parameter space, this is the equation that describes gradient flow. So theta dot is determined by the gradients of the loss function, L, where L is this empirical loss that I wrote down initially, that's constructed from your finite number of data points. But it's informative to think about that as coming from, there's a contribution that comes from the kind of dependence of the loss on the function, and then the dependence of the function or the model on the parameters. And so just breaking that down via chain rule, you would write it in this form. So f of x sub alpha is the value of the model output. Here, I'm just taking it to be a scalar output at the moment for simplicity. But there's a dependence of the loss on the function directly, and then the function itself changes because the parameters evolve, and that's captured by the second term. If you like, in the back of your mind, if you're thinking about, say, squared loss for training, then DL/DF is linear, is something that's linear in F, and we also have this target here, which are the Y's. So if you think about then, given this there is some gradient flow that happens on parameter space, or some evolution that happens on parameter space. What evolution in function space does it give rise to? You can plug this equation into this over here, and plugging in basically for theta dot, you get this thing that is written mostly in terms of where the dependencies on the loss in the function and the function in the parameters are factored out into two separate pieces. So again, there's this first derivative, and then there's this part which is just coming from how the learned model depends on the parameters, and the parameters themselves are changing. Because of the form of this is an inner product. It's a contraction over the mu index. So you're taking derivatives of the function with respect to parameters, and then summing over all the parameters. This is, again, a two-argument function. It holds a special place in the dynamics. So let me just define this quantity, theta, big theta sub t. It's a function of two arguments, x and x prime. And it's just gotten from a contraction of the model gradients over all the parameters in the network. In general, it's a dynamical variable because these gradients change with time. It's also a random variable. And so this, if you could know something about this function, you could then kind of plug in to this equation and solve. For instance, because if you're working with squared loss, this term would just also be linear in F. In general, this is difficult, but again, amazingly, there's simplicity that arises in the infinite width limit. So it turns out, for reasons that I won't have time to get into, but really how the different scales of the problem, scales of these different factors enter into the problem, it turns out that this dynamical variable doesn't evolve at all. It's just frozen at its initial value. And so, theta t is equal to just theta naught. And if you plug that in here into this equation, and in particular, treat the case where you're solving for squared loss, that's something that is just a linear differential equation, and you can solve it exactly. So that's kind of what happens in function space, and there's sort of an effective model that holds in parameter space also, which corresponds to basically just doing a first order Taylor expansion of the function about it, the initial set of parameters. So that's F naught. And just expanding to leading order, that turns out that this function, the training of this function is equivalent to the solution you would obtain via this function space analysis. So this is sort of the effective model, or the thing that's effectively the relationship between F and the parameters that is holding in parameter space. So this was kind of a work by a bunch of folks. We did analysis in parameter space. There was a lot of work on the function space side also. And as I mentioned, it's, although I didn't get into the details of it, it's interesting mechanistically why it happens. And it's something that really comes from the different scales of the initialization, how they enter into the problem, and the setting of the learning rate and so on. Because with tuning of these other scales, it's actually is possible to recover different infinite width limits than the Gaussian process. So there's been work in the literature on other kinds of limiting solutions, other mean field theories. This is the one that is most, I think, applicable to practice because it comes from how we usually initialize models. Yeah, but I mentioned that just to point out that there's a literature out there on this topic. So that's the exactly solvable model that you get from infinite width. And it's then can be a starting point for other theoretical analyses. So one thing that we did was we studied this problem again in wide networks, but found that this correspondence breaks down if you run gradient descent above a critical learning rate. So for this model to basically hold this effective first order Taylor series, the learning rate needs to be smaller than a critical value. If you drive it above that, there's kind of a transition to a different region of the parameter space or the function space, and we have some handle on that understanding of that. That comes up in networks that have fixed depth but are pretty wide. So again, in this wide limit, just thinking about the width and the learning rate and how those affect kind of the dynamics. But since then, there's been also a bunch of work on other treatments, perturbation theory, and also other just theoretical treatments, like getting some exact solutions also at finite width. So I will just point out this literature and still kind of, it's an area of ongoing research for kind of computing corrections, either with finite width or finite depth over width, and so on, to these things to get a more accurate model of the dynamics. And so in general, I will say the kind of picture is that there is some maybe broader phase diagram of the dynamics in deep neural networks, and where you sit in that diagram depends on the depth, the width, the data set size as well, and the learning rate. And so, certain parts of this phase diagram are controlled mostly by this exactly solvable limit that I described. Other parts might be controlled by this other type of dynamics that you transition into in number one, and yet others kind of might be controlled by other regimes. So I think that's kind of an area of active research still, and open questions kind of surrounding that. So just to summarize this part, there are a lot of lessons that we've learned from the infinite width limit. And in fact, I'll use this, one reason for introducing this is that I'll use this exactly solvable model as a case study in part 2, where we look at scaling laws. But one of the lessons that we've learned was that infinitely many parameters is not a problem. This is something that kind of went against, was sort of an open part of the open mystery of deep learning at the time, was why you could make models very large, heavily overparameterize them, and yet the complexity of the problem was not exploding as you did that, and you weren't getting significant amounts of overfitting. And so with this kind of result, we know now, at least when you make the width wider, your complexity is kind of controlled. You're moving towards the Gaussian process, and that's sort of fairly simple as a starting point for initialization. And then also the dynamics is fairly restricted because effectively the problem is quite regularized. It's just a convex problem. You're not exploring the full kind of landscape of optimization. We reduced a complicated problem to a simpler problem. So now, like all of the questions that had to do with generalization, you can ask about these linear models with these particular sets of fixed features. So I'll refer to these kind of interchangeably as random feature models. That just refers to the fact that in this model, there's a linear term, linear in parameters, and the actual features that you're using are these things that are just evaluated at initialization. So the features are not learned during the course of training. That's why this is not a feature learning regime. They're frozen, but there is some nonlinear dependence still on X in this problem. So you learn complicated functions, but the dependencies on the parameters is quite simple. This is a class of models that's well known in machine learning. They're referred to as kind of random feature models. There's other insight that you can gain from this limit. For instance, from these exact solutions, you can see that simpler functions are learned first during the course of training and so on. And this is referred to now as spectral bias. And all of these, as I mentioned, they're really statements about effective dynamics or effective optimization. So they weren't statements about the global landscape that is potentially there, that is there in the infinite width limit, but just the region that I actually end up exploring because of some kind of implicit constraints in the dynamics and coming from the initialization. Okay. Any questions maybe for this part before I move on to part 2?
Are there any questions out there for Yasaman? There was one in the chat.
Why aren't the variances for the biases also scaled down by n? Because you don't, so what's important is per hidden node, that the variance of that be order 1. And so coming into a hidden node, there are many contributions from different weights. There are n contributions, but there's just one bias. And so the weights need to be scaled down, but the bias just, it's like a scalar a single contribution. And then how wide is pretty wide? So that also, I think more recent work has kind of shed light on that. In practice, so even in theory, it depends on the ratio of the width to the depth, but also width to data set size. So practically speaking, when width is sort of the largest parameter in the problem, so like depth is fixed, width has to be pretty large, and data set size relatively has to be pretty small. That's when this solution starts to kick in. Also, the learning rate has to be below the critical value that I mentioned, which often happens, but still is a constraint. What do you mean exactly by simpler? So that's work really done by other people. So there are a bunch of references out there, but one sense of simple that has been studied is, for instance, let's say kind of in terms of like a Fourier series expansion, or if you did an expansion in spherical harmonics, you learn kind of the lower frequency functions first before learning the more oscillatory complex ones. So that's one notion of simplicity that's been studied, because you can use these exactly solvable limits there. And there are others out there also, different notions of complexity.
Any other questions for Yasaman before she continues?
Okay, if not, I'll then now focus on some more recent work done with really great collaborators. So Ethan Dyer, Jae-Hoon Lee at Google Research, and Jared Kaplan and Udkar Sharma at JHU. So what are scaling laws? They refer to kind of the observations coming from a bunch of recent empirical work where practitioners have gone and measured how neural network performance improves as a function of some basic variables. So if you look at the test loss, or if you looked at the test error, what they found is that you get pretty smooth scaling as you increase the amount of compute, the amount of data that you use, and the number of parameters. So this is one example coming from scaling laws in very large language models. So it's not surprising that as you increase the amount of data, for instance, that your performance will improve. And there's a lot of old work on, of course, this is the thing that's of primary interest in machine learning, just studying generalization performance as a function of amount of data and other factors. But to differentiate this from maybe some of that work here, we're trying to understand empirically why you get such smooth scaling over many different regimes, and trying to match a bit more to experiments what these actual numbers might be. So what governs these numbers? We're not just looking for, let's say, an upper bound that guarantees that performance will improve as you increase the amount of data, but you actually want something that we would like to have maybe more theoretical insight into the typical case. What sets these numbers? Why are they such smooth, kind of clean power law trends, and so on? And is there any relationship maybe between these different types of scaling? So this is interesting. Even on the empirical side, it's still being explored because it means that a lot of the, for instance, a lot of the complexity and model design choices and algorithmic choices that you have in deep learning may not actually, it's not clear how, if they're actually transferring over. So like you maybe take two different architectural classes and you find that maybe they have similar exponents, so maybe they have like parallel lines in their scaling, or maybe they cross at a certain scale, which means that, you know, the architectures that we think are for some data set very good today, tomorrow, if there's more data, actually this other architecture would outperform, and so on. And so kind of always I think these things are just, even on the empirical side, important to study, because when things are reported in machine learning, we're basically just taking a single data point on this curve and talking about, with, you know, this fixed benchmark and fixed amount of data and fixed model size, what is the performance? Really, we want to mod out this direction that comes from these extrapolations and kind of understand progress in the direction that's orthogonal to this, although that's like a bit hard to define. So empirically, that's kind of, I think, the perspective for why scaling laws are interesting. They've also just been practically useful. So these measurements were used to inform kind of the most efficient way to scale up, like scale up a large language model to the largest size. So GPT-3, which came out, you know, semi-recently, one of the things that they did was took these measurements and thought about what's the best way to, you know, devote divvy up, let's say, compute and parameters, so as to get the best model that we can. So our interest in this was more on the like basic science side. Can we better understand why these trends emerge empirically? What features of the data and models determine the exponents? And again, this ties into the study of generalization, which is you know, a major area of focus in machine learning. But we're trying to see if we can say anything stronger than that would actually have some kind of bearing on empirics and kind of typical case analyses. We'll see that at least we made some progress on this problem. We don't have kind of a complete and very super accurate or fully predictive theory yet, but we'll see that in some regimes there's we can actually at least categorize some of the exponents or where the scaling is coming from. In some cases, there's a universal exponent in terms of its numerical value on some problems. And in other cases, it's less universal. We'll examine a setting where we have full theoretical handle on the problem. And this is drawing from the earlier part of the talk. We'll analyze these models that come from this infinite width limit perspective. But so these are, again, the random feature kernel models, linear models that you can construct. In that case, we have a full handle. And then in the more general setting, we propose kind of an expansion, and then we'll try to empirically test the connection to other quantities that we can measure. So the setup here is for our focus, we just looked at how do things scale with the amount of training data and how do they scale with the number of model parameters. So there are two variables that we're scaling up. And when I say number of model parameters, really I also just mean mostly, in most cases, it's going to focus on scaling with layer width, where width goes as square root of p. And that's because, again, we have this theoretical handle from the infinite width limit and corrections to that. And that's the reason that we're able to say more there and not for the more general case. So the quantity that we're interested in, just setting up what is the test loss, it's taking kind of the learned model, f hat, which depends on the data set D, depends on the initialization theta naught, evaluating that loss on the population distribution, P. So this is the test loss. And then averaging over the draw of the training data set and the choice of initialization. So in general, the test loss would depend on that particular data set that you chose. We're looking at an averaged quantity here that's averaged over that, but this will have, L here will have some dependence on the amount of data, D, and the number of model parameters, P. And so the kind of expansion that you can keep in your mind is that L of D has some bare constant. If we just look at its D dependence, it will have some bare constant C infinity, and then some hopefully power law scaling, if we believe the numerics, with exponent alpha D, and similarly the P expansion. So when we were thinking about this, we came up with a classification of exponents that's tied to their origin, just as a first pass of thinking about how we were going to try to explain where exponents came from. So we kind of came up with two categories, and we named them as follows. One we called the variance limited regime, and the other we call the resolution limited regime. So the variance limited regime, roughly speaking, it originates from fluctuations when you're smoothly approaching a limit. And it gives rise to this integer exponent equal to 1 asymptotically. So I'll say a bit more about that in a few slides. But that's separate then from kind of what we think is the picture in this other regime, which we call resolution limited. And here, as you'll see when I define when these regions actually occur, the rough idea is that in the resolution limited regime, you're studying the scaling as a function of a variable that's not a bottleneck in your problem. So we have these two variables, D and P, and we're going to only study them in kind of regimes where either D is larger than P or vice versa. That's where we kind of have a handle on this problem. We don't have too much of a handle on the intermediate regimes, crossover regimes. And in the setting when, let's say, D is smaller than P, D is your bottleneck variable. And then D is the thing that's helping you to improve some resolution of your data manifold. That's sort of intuitively the picture that we have of this, what's happening in this regime. And this gives rise to kind of non-trivial integer exponents that will tie back to some more microscopic quantities, but it's non-universal only in the sense that it doesn't take on a fixed, say, integer value. It does depend on other quantities that then can be evaluated. But yeah, I'll get to this in a couple slides. So just to flesh this out a bit more, again, for what the definitions of these two regimes are, variance limited means you fix one of the variables, one of D or P, and you're studying scaling as a function of the variable that's larger and growing. So for instance, let's fix D, let's take the limit where P, let's study the regime where P is larger than D and study the P scaling that's coming from that. So we're not bottlenecked by P in this setting. We're really just studying the fluctuation. It'll end up that we're governed mostly by fluctuations of P as we smoothly approach some limit. And vice versa. Let's say we fix P, we take D to be larger than P and we study the D scaling. That's the definition of variance limited. And so if you look at a 2x2 table where we're either studying scaling with D or we're studying scaling with P, and then we classify whether D is larger than P or vice versa, which is under and over parameterized, then in this 2x2 table, variance limited will sit on the diagonals. And by our definition, resolution limited will sit on the off diagonals. So again, resolution limited here means that take one of D or P to be large, it's not a bottleneck for your problem, and you study scaling as the function of the smaller variable. And so these are these off diagonals. So empirically, if you went out and tried to get some observations of this, this is what you would find. So this is that 2x2 table that I showed from the previous slide. The diagonals are studying the variance limited regime. The off diagonals are studying the resolution limited. And what you see, what each of these plots is showing the loss or the loss with the bare constant subtracted as a function of data set size or width across different data sets, different models, and different loss functions. And so variance limited, as I mentioned, kind of regardless of these different factors, data set, model, and so on, you see that the exponent is kind of close to 1 empirically. And then in the resolution limited regime, you see that the exponents in general kind of vary for the different problems. Here where you start to see deviations, this is just an artifact of the numerics because empirically what we do is, I said resolution limited. To be in that regime, you have to have width much smaller than data set size. So data set size is effectively infinite, but in a real experiment, at some point you kind of get into the crossover regime where width and depth are of the same order because these were done with finite size data sets. And so that's where these deviations start to come in. But you kind of see fairly cleanly that kind of when one of the variables in any of these regimes where one of the variables is much smaller or much larger than the other, that you can kind of tap into these different categories. So what was the basis for this? We started by kind of studying pretty closely a concrete case, which is the student-teacher random feature setting. So again, that's this case of where we have these models that are linear in the parameters, but use these nonlinear features that come from a neural network at initialization. And we have a student-teacher setup. So there's a teacher model that generates the data, and there's a student model that learns from that. And in that setting, we can get explicit derivations for all 4 of these regimes that I mentioned. We can do additional things like in this setting, we can relate the exponents to the properties of the kernels that you get from these random features. And you'll see that it's really the power law decay in the eigenvalue spectrum of these kernels that then ties into kind of the exponents for the D and P scaling. We also find that in this setting, there's a duality between the model and data set size analysis because you end up using kind of similar matrices to construct that enter into the expression for the error. And so the exponents for model and data set size scaling turn out to be the same. And we'll test some of these predictions a little bit outside this framework and in the setting that is very realistic in practice where people have pre-trained models and then fine-tune on small amounts of data. And then I'll talk a little bit about the more general setting where we kind of use these ideas to posit, particularly for the resolution limited regime, posit an expansion and then try to test it. For the variance limited regime, it's on a sound footing and we have a formal proof, but for the resolution limited, it's a bit of we kind of posit that something happens and try to test it. So I think since I'll try to speed up a little bit. So I'll just say a few highlights that come from this concrete case study. What is the case study? So as I mentioned, there are these teacher and student models where the teacher generates data. It's some function f of x that generates data from some fixed set of features f sub m that could be neural network features. And then the student model is a linear model constructed also from random features that have some relationship to the teacher features. So they're just, they're obtained by taking projections of the teacher features. So you're working kind of in the same basis for this problem, drawing from really the same collection of features F sub m. And then you can write down, because everything is, these are linear models and you're doing squared loss, that's the setting we consider, you can write down exact expressions for the test loss in terms of various Gram matrices and these projection matrices and try to extract the leading term. I'll just say kind of the result, which is that you can, for the variance limited case, you can extract the exponent equal to 1, and it comes from fluctuations of a finite size covariance matrix about its limiting case. For the resolution limited regime, you have to input some knowledge of the kernel into this analysis. And so then we take what I'm going to try to argue is a good physical assumption that the power law, that the spectrum of these kernels, if you look at the eigenvalues lambda sub I, they decay as a power law when you look at real data and realistic kernels that are fairly generic. And so if I call that exponent 1 plus alpha k, putting that as an ansatz into those expressions, you get that the data set and model size scaling are both governed by exponent alpha k. And so you also get in this particular case that the exponents are the same. That's special to this setting, and it doesn't hold in the most general neural network setting, but it does hold in things that are kind of close to this setting, as I'll show you in a minute. But now we kind of have then kind of a connection between the exponent of the kernels, of the kernel spectrum, how that decays, and the exponents that govern data set and model size scaling, at least from this simple setup. This is just a numerical check, basically a special case of the empirics I showed you earlier. So I won't spend a lot of time on it, but it shows again this variance limited regime and resolution limited in these in this particular setting of linear student teacher models. And to kind of study different types of data sets, what we did was, or to smoothly change kind of the exponent for this problem, we downsampled data sets. And you can see that that has an effect, again, here in this resolution limited regime as we expect, and not in the variance limited regime. Now, regarding this ansatz for power law decay, here's an example that shows you that the exponents at least kind of asymptotically look like a power law. And again, this is for real data on random features that come from a neural network. So this we think is pretty generic. Smooth kernels, sufficiently smooth kernels have a bound on their eigenvalue spectrum. And we think that if there are no other kind of constraints on the kernel and it's kept rather generic, that probably this bound is generically saturated. And so we think this is maybe a more general thing, but again, here in this setting, you see that the power law and the eigenvalues gives rise to these power laws here asymptotically, and we can measure these exponents in numerics and see that they match and are governed by alpha k. So here now is an empirical test of something that lies outside the framework we just studied, but we still see that some of the results carry over. And so this is it's a pretty realistic setup. You take features that were taken from a pre-trained model on ImageNet. It's a pretty large data set. And then we use it to extract features for CFAR10 and then construct a linear model on top of that and just fine tune for CFAR10. So this pre-training fine-tuning kind of setup is quite common. And what you see is basically because so the reason it connects to the previous analysis is because we are training a linear model, but it lies outside that analysis because we're using kind of learned features rather than random features in the setting. But still we see that this duality or this equality between the alpha p and the alpha d exponents holds. So here, if you look at the off diagonals, alpha p and alpha d are pretty close. And again, you see the variance limited exponents equal to 1 in these diagonals. The difference between the left and the right hand plots, for people who are kind of very familiar with this literature, has to do with the regularization. So there's something called double descent that happens if you don't tune the regularization quite right. And so actually, this regime that we're studying for resolution limited lies to the left of this double descent peak before we transition to another regime over here. So that's maybe kind of in the details. Those peaks go away if you tune the regularization. But we do see evidence of duality even in this realistic setting. So now just to jump to kind of the general setting, I won't say more about variance limited because we have kind of a full handle on that, and I can refer you to the paper for more details. It comes, for the large width case, it comes from knowing about the finite width corrections to the infinite width limit. So we do use that in the analysis. Instead, I want to talk about what I think is like the regime we're most often in practice, which is this resolution limited regime for general neural networks. And again, as a reminder here, what's happening is that you take one variable to be quite large, and you're setting scaling with respect to the bottleneck variable. And I tried to kind of paint a picture that what's happening with that smaller variable is that you're better resolving a manifold. So this is quite natural, kind of if you think of P being quite large and D being small. So when you think about an overparameterized model with D training points, these training points kind of provide interpolation points on the true data manifold. So when you train, you kind of, if you're able to fit exactly on the manifold, then you have those points. And then the more points you have, it will kind of control your fluctuations or how far you are on other points that are not the training points. So the error at test points is often controlled by, let's say you have a point over here that you're trying to study that's not a training point. If you've pinned to the correct function value at the training points, then your deviation kind of at that new test point is controlled by the distance on the manifold and other properties of the function. So this picture is sort of the natural one. It's an older picture also for how data set size scaling or what the effect of adding more training points is. We think that the same picture kind of holds if you flip the variables also. So now, let's say D is quite large. You have a lot of training data. So you basically have access to almost the true data manifold. And what you're doing is studying scaling with P. Now, so you're limited by the capacity of the model and your ability to fit. And every time you add P, it appears that you kind of have an extra degree of freedom to fit the manifold. This is just a picture. I'm going to, from the numerics, I'm going to try to convince you that that picture is semi-accurate, but we think there's like sort of a dual relationship between these two things. So with that picture, kind of the rough idea is that if you want to then study the error at a test point, you can expand about in this asymptotic regime where D and P are both quite large. You're going to expand kind of the error at a test point in terms of function values at the nearest training points. And so if you do that, if you make these assumptions and make an assumption that you have kind of optimized, you're at the minimum of the loss function, and you do this expansion of loss at a test point X about the nearest training point, then you see that, first of all, this expansion generically starts at exponent m equal to 2. For piecewise linear functions, that term drops out, and generically it starts at exponent equal to 4. But also you see that it's dependent on kind of these coefficients and the distance between test and training points on some manifold. Now, I haven't told you in which space X to do this expansion, and I've been a little bit sneaky about that. I'll say how we make measurements in a moment, but basically, if you do this expansion, you see that there's this dependence, and if you kind of posit what is a reasonable model, which is that this distance between test and train is the thing that is changing as you change data set size or model size. So going back to this, as you increase amount of data, you're decreasing the distance between test points to the nearest training points. That often goes as a power law as well, if you were to look at empirics. And so that nearest neighbor distance kind of decreasing with D or P. And that depends, I should say, on the dimensionality of the manifold that you're considering, just because of kind of like the cursive dimensionality argument. So this is like a back of the envelope sort of argument for why this quantity itself would scale with as D or P inversely. And so that would give rise to kind of a power law scaling for L. And so you might just as a first hypothesis kind of say, okay, something like L goes like D to the minus N over D would hold at leading order in D, the data set size. And similarly for P scaling. And generically, this would start at N equals 4. So the prediction is sort of that something like 4 over little d, where d is the effective dimensionality, would give you the exponent asymptotic, would describe the exponent asymptotically. And similarly for looking at the parameter scaling. So, and indeed we went out and tried to test this. What we did was try to estimate little d by looking at the power law scaling of nearest neighbor distances from the last layer of the trained network. And if you do that, so you get an estimate of dimension on this x-axis, and then you can independently measure the exponent alpha d from scaling laws and try to match, and you see that there's some kind of rough agreement to 4 over alpha d for some models, and then kind of a range of things outside of that. So somewhere between kind of 2 over alpha d and something else, you see that there's kind of a rough correlation between alpha d, inverse alpha d and the dimension. Something like this also holds for model size scaling with dimension. So now this is from earlier work by Sharma and Kaplan, where again, they made measurements of this effective dimensionality of the data manifold and compared to the exponent. So the picture I've tried to paint in this more general setting is that there's a relationship between the resolution limited exponents and an effective dimensionality that comes from kind of the learned feature space that is represented in the model. And so there are relationships basically between these D and P exponents, the effective dimensionality, and then also from that simple setting, the teacher-student setting, also the kernel eigenvalue spectrum. And so there's kind of like I would say a more general graph of connections between these 4 quantities that we've tried to highlight in this resolution limited regime. So just to close, we have a categorization of these exponents based on the mechanism, based on their origin. So in the variance limited regime, we get a common exponent that's controlled by fluctuations as you approach some limiting value. In the resolution limited regime, you get something that's non-integer in general. It depends on the the data manifold, and how well the model is able to learn that data manifold. It's controlled by these kernel eigenvalues and the effective dimensionality that I mentioned. And we only have a handle in this setting on these kind of non-intermediate regimes. So either D is larger than P or vice versa. And crossover regimes, we don't understand as much. This was kind of just to try to understand, see what we can say about scaling laws in practice for neural networks. But I'll say that there's also now kind of more empirical evidence emerging that sometimes scaling laws break. And these are some of the most interesting cases because that's, when does a model have exhibit a transition in maybe like a phase transition in performance, and when does it not, I think is an interesting question, because ideally we would like to have things be predictable. With scaling, we make them we can kind of understand what's predictable. And then there are these other regimes like the one on the right over here, taken from GPT-3, where you see that only above a critical model size does the model actually start to perform well. That's even less, that's not understood at all at the moment. And so that's kind of, I think, a next frontier. Yeah, and thank you for your attention.
I'm sure lots of people are out there clapping behind their microphones and videos as well. Yasaman, thank you for the wonderful talk. I'm sure there are many questions. Please, if you have a question, just feel free to unmute yourself and ask it. Maybe.
Hi.
Go ahead. Yeah.
Hi, Yasaman. Good to see you.
Hi.
I have two questions actually. So the first one is related to the scaling of DMP. So if you scale D, you improve with the power law. If you scale P, you improve with the power law. So that would actually imply that if I had a model where I gave it more data and more parameters, so I kept D over P fixed, the performance would stay constant. So have you looked at this? Because if this was actually true, you would know that it's really just only these two parameters that enter versus some other effects that might distort this.
That's interesting. No, we have not looked at this. I know of maybe one empirical work, I think, that maybe touches on this, where they've tried to look for contours of constant loss as a function of multiple variables, maybe DP and perhaps some others. And I think that maybe is consistent, semi-consistent with what you're alluding to. But we ourselves have not.
Do you have the reference for that?
Yes, I can send it to you.
Yeah, thank you. And my second question was about, I know this was not really what your talk was about, so I really just want to hear your opinion on it, if you have any. Do you think there's a chance of addressing the constant that you call C infinity? So this, I mean, is a theoretical limit on how well a model can possibly perform if I throw it infinitely many data or infinitely many parameters. And of course, this will be a function of the network architecture and will be a function probably of the problem itself. But is this something that you could sort of study if you understood the data manifold well enough and the Bayesian of attraction of your loss function? Could you somehow attack this question of sort of which problems can be machine learned, or which problems, so which architectures have a limit to it where you just can't improve beyond anymore?
It's a very interesting question, and I don't know that I have a lot of insight into it. I would like to understand it better. I will say, I think maybe if you had a very concrete model of the data manifold or the right physical assumption, you could try to tackle that. But I personally have not yet tried to investigate that. But it's a great question, and I don't have a better answer, I think.
Yeah. Thank you very much.
All right. Any other questions for Yasaman? There's one in the chat. I'll ask it on behalf of Tess because I think she had to step away to something else. Tess asked, would you expect scaling laws to differ for equivariant architectures, or does it only depend on the data?
Yeah, no, it totally would. And actually, I should say, so then maybe to clarify, when I said it depends on the data, it was really a feature of the learned model that when we were talking about the effective dimensionality. So that's coming from a learned model, or the kernel spectrum. So I talked about it in the random feature setting, but also in the more general neural network setting, you would look at the kernel of the learned model. And that that incorporates both the data that you're trying to learn and how good of a match it is to the model. So definitely the model itself is playing a role here, how well it's learning and so on. And yeah, so there's been some work on this. And certainly if you have symmetries in your model that are enforced, you get kind of an improved rate for the scaling laws by a factor that relates to the kind of size of the symmetry group and so on. Yeah, so for sure, that's theoretically what's expected, and hopefully it's observed in practice if everything is working. Yeah, that's a great question.
Yeah, wonderful question. Thanks for the response. We have a question from YouTube. Nicolo asks, you briefly mentioned the double descent pattern. Could you discuss the connection with these scalings a bit further? I guess the scalings on the left and on the right of the peak are different.
Exactly. Yeah, that's perfect. So, so here, when this was the place where without proper choice of the regularization, you see double descent. So let's say we focus on this one, we're setting descaling. We have different sizes of P, let's say 1. So double descent happens when you have this D on the order of P crossover region, and that's this peak. To the left here, we have D smaller than P. And we're setting descaling, so that's resolution limited. And then asymptotically over here on the right, actually we approach variance limited regime. So not here, this is still kind of transient, but if we were to take this out further, you would actually see then a recovery of the exponent equal to 1. So variance limited and resolution limited are exactly kind of on the two sides of this thing, and double descent, which is this intermediate regime, is in the middle.
Wonderful. Those are all the questions on YouTube. Any other questions for Yasaman?
Yeah, I have a question. So if I've understood correctly, this explanation for these scaling laws is that the network is almost like, I don't know, memorizing like where to sort of map points on a manifold, or at least this is like a part of the explanation. And I'm wondering if there's like a tension here with like this description of like what the networks are doing in some sense with like kind of the empirical fact that they like generalize in interesting ways.
Thanks for that question. So maybe I should clarify. I'm not sure I would call it memorization in this case. So here, really, the distinction between memorization and learning is more subtle and I think different. Here, what we're really just doing when we do empirical risk minimization is we're trying to have low training loss. And let's say we're trying to do squared error. So then we're trying to actually fit the function value. So whether internally the model is like what it's learning, however it's doing that, as long as it's fitting the function values, that's learning and that's prediction. And so it's not memorization. Like I guess two models could both fit function values and we don't know internally what's going on, but they're both, one could be a good model, one could be a kind of bad model. Let me go to this. So, when we say, I guess I should say then we're working in a regime where we can do interpolation. We're fitting the true function values exactly. So there's like no noise coming from these training points. If you learned the noise, then you would be kind of worried more about the generalization and memorization of the noise. Say individual training points had some noise that were not reflective of the true distribution of the true function values. But in this setting, we are like, the setting I talked about was one where we have, we're doing interpolation, we have access to the true function values, and then the test error is just controlled by kind of this distance and the fluctuation. So by knowing that I fit the true function exactly at these points, I can know about kind of the deviations in the function values away from these points. I think we could easily incorporate, it was just not our focus, but we could incorporate the effect of training noise. Like if you add, if your generative model for the training data, something like some function value plus, say, Gaussian noise, which is often added as a generative model, then you could kind of incorporate that and see that as how that comes in. I don't know if that, sorry, hopefully that was useful.
Yeah, thank you. Yeah.
Yeah, but thanks. So this is, we're learning the true function values exactly in this, in the pictures that I was talking about.
Other questions for Yasaman? I have one, and maybe it'll give other people a chance if there's more. So I know that people have been trying to overcome this spectral bias by trying to, in the NTK, use Fourier features to manipulate the spectrum and things like that. You say that in certain regimes, there's this connection between the kernel and the spectrum, sorry, the kernel spectrum and the scaling laws. Have you tried really engineering those and perturbing them and seeing changes in the scaling laws as you perturb the spectrum?
Yes, in this limit, like, so this, in this setting, which is kind of, it's real and not real at the same time. So this is like the random feature setting, but it's real data. You see that if I change the kernel spectrum here, so we artificially change the problem here by coarse graining, let's say MNIST. What that does is that downsampling kind of changes the effective dimensionality of the true data manifold, and then it changes the kernel spectrum also. So the blue to the pink kind of curves is that change. So that was the knob. We did this precisely to like be able to have a knob where we change the kernel spectrum and then see that the exponent changes.
So that was the knob. I think I missed it. That was the knob by which you uncovered the relationship.
That was the knob, but this is now tested in the random feature setting. I think it would be nice to have more tests in the neural network setting, so, or more general setting. So for that, you would look at the kernel spectra of a trained model, which is also power law, and then see that that's reflected. I think that's maybe the one missing piece in the most general setting to between. I made a connection between the exponent and effective dimensionality. There's a final closure to that, which is the exponent in a real model, real trained model eigenvalue spectrum.
I see the spectrum dependence on the of the scaling law in the neural network case. Sorry for all the words. So the scaling of the eigenvalue spectrum. Yes.
Coming from a learned kernel.
Yes.
And how that relates to the exponent.
Okay.
That which is kind of just it's almost this, but it's a learned model rather than random feature.
I see. Very good. Thank you. Any other questions for Yasaman? All right. Well, if there's no further questions, let's thank her one more time. And Yasaman, thank you. We really appreciate the wonderful talk. We will post it on YouTube before too long, and hope to see you before too long. Thanks a lot.
Yeah, thank you again for the invitation.
Guess we can stop recording.